Thanks very much to the organisers of this for asking me to give this tutorial, as it's been called, this afternoon. I just want to point out before I start that this is going to be only looking at binary sex or gender. And I'm not going to think at all about non-binary. And I do it really without really apologising, because it's not where I've done my own research work. But it isn't impossible by any means to generalize from what I'm going to talk about today to the more general issue of non-binary sex or gender, or indeed continuous elements of sex and gender. Anyway, that's just a note at the beginning, so you know where we're coming from. So I've got two aims: to show effectively how you design studies, but mostly it's going to be about the way you analyze studies. And partially that's because Cara has already covered some of the design issues, but I will briefly talk about design. And I've said the second point already. Oh, intersectionality I haven't mentioned. That, again, you can fairly easily generalize what I've been saying. There are actually real tools being developed these days to look at intersectionality, but that really is a topic of its own. Okay. So the basic issues in design is, and it's obvious, the first one, you need a good number of both females and males if you're going to adequately look at the difference. And indeed, to adequately find out the results for the two different sexes, you obviously need a decent number. 50% women, 50% men is sort of a first starting point. I say there that it's a good target. I think I'd say probably it's a reasonable target to have. But in real life, the practicalities actually almost always rule that out. I mean, I've been involved in many clinical trials in the last 20 years, and I can't think of a single one where there wasn't a struggle to get enough people into the trial. So you're not going to say, well, we're not going to have you in a trial because you're a man and we haven't got enough women. You just got to get your quota up to be able to have the power for the whole study. Also, it's not necessarily true that having 50% men and women is going to give you equity in terms of the effects that you're going to see, you're going to be able to estimate for the two separate sexes. Because women, if we talk about cardiovascular disease anyway, women have lower rates of cardiovascular disease at all ages. So you need a larger sample of women to be able to get the same degree of power, because the power will depend upon the number of events you have. So 50-50 isn't necessarily the most efficient way of doing it. And also there's another argument that says perhaps you should have a recruitment which mimics the population in general. So if you're doing a stroke trial, you should have as many women in as there are women with stroke in the community at large. But of course there's problems with that as well, because you could think about, if you take an extreme example, if you're going to look at breast cancer, where males can have breast cancer, but if you try and think about how you do the 50-50, you wouldn't be able to do it. But if you're going to wait long enough till you find enough men to put in the trial would, again, probably go on too long. The last point is a nuisance, really, because you would think that if you doubled the sample size, I mean, notwithstanding what I just talked about, the different power for men and women, which is quite often the case, but even if you forget that, even that isn't good enough if you want to look at the interaction between the two. So if you want to estimate what the difference is between men and women in terms of the cardiovascular risk, the cancer risk, or their hypertension prevalence or something, you probably need more than double the sample size. And the reason for that, I think, is, again, pretty obvious when you sort of think about the problem. If you're trying, when you're analysing a study, you try to get enough people to have power to find something like, let's say, a 10% difference in the intervention compared to the control group. But when you're talking about sex differences in the effects of drugs, in that same sort of example, you wouldn't look for a 10% sex difference, because that would probably be much higher than you could ever really think would be the case. It may be possible, but it's unlikely. You'd probably want to take something which is much smaller. You'd expect to see a smaller sex difference than you would an overall difference between the intervention and a control in a standard clinical trial. So you probably need even a larger sample size. Almost certainly you need to have at least 4 times the basic sample size that you would for a trial where you don't take account of sex or gender. So it's bad news, I'm afraid. You've got to put up with the fact that you're probably not going to have enough power to do a subgroup analysis by sex, unless you've got a really large study. Or if it's a cohort study, a really large population, like the UK Biobank of 500,000, for example. However, what you can do, and what you should do, is to disaggregate the results by sex or gender, and to publish those results for future meta-analyses. Because there's hardly any drugs on the market where there isn't a similar drug, at least in the future, soon after the first drug has been introduced. So even if you can't do it today, maybe 5 years' time, you can do a sex comparison with sufficient power. And I'll come on to meta-analyses at the end. So disaggregating and publishing those results, even if it's only in the supplement to the paper, at least then you're giving people a chance in the future to do what you haven't been able to do, which is to find evidence which is going to influence and satisfy people to know whether there's a sex difference in the way a drug, in my example, works. The other point I've said is be careful not to overstate your findings. One of the problems I feel with sex and gender research, especially thinking about women's health, and before I say this, by the way, I'd like to point out that this centre that we're trying to set up is not for women's health, it's for sex and gender, including men's health. Anyway, but if you're trying to look at women's health, to give my example, if you find that there's a larger effect in women than men, but you haven't actually seen whether it's significant, if you like to use p-values, or a sufficient size, if you want to think of it in a more clinically useful setting, don't overstate it. You may find that women have got a higher risk, but that may be just a numbers thing. Perhaps there's more women in the study than men, for example. Okay, now the first issue, so I'm going to think now about doing a new study, which is where you want to have a comparison of the sexes at the end of the day. You've got 2 types of analysis that you might want to do. So I'm going on to the analysis side now, and the rest of it's going to be mainly on analysis. You've either got the continuous thing, and my blood pressure is my example I'm using there, or you've got a binary thing that you're interested in. When I say thing, I mean the outcome. So instead of blood pressure, it could be the risk of a heart attack, or it could be the prevalence of hypertension, which is binary, not continuous. If you, on the continuous scale, you can look at means, t-tests, if you're not going to think about confounding variables or multiple regression type things. And if you are going to look at confounders, you want multiple linear regression. If it's binary, you're thinking about proportions or percentages, which is the same thing, multiplied by 100. Chi-squared tests, if you're not going to take account of adjustments. And multiple logistic regression is probably what most people would use. So the first thing you've got to think about when you're doing analyses is which of the 2 is it? And in any one study, of course, you could do both. You usually would. I'm going to concentrate on the binary side. I'll come back maybe at the end if I get time to talk about the continuous side. But let's just think about the binary side. So let's suppose we've got a binary outcome we're interested in. So the trivial example, the trivial context, is when you're directly comparing females to males. And my example for that is heart disease more common in women than men? Is the question. So it's a binary outcome, heart disease, and it's a binary exposure, it's men or women. So analyze it as a relative risk. So the risk is the number who get the disease over the starting number. You take the risk for men and the risk for women, and the ratio is a relative risk, which I'm sure everybody knows. And it's confidence interval. Being a statistician, I've got to emphasize everything should have a confidence interval to show how uncertain you are. I'm not really particularly keen on p-values, so I always emphasize a confidence interval. The more interesting context, the one which I'm going to concentrate on today, because it is more interesting, is when you want to compare the actions of some factor, like a drug, on some outcome, like heart disease, between the sexes. So if you're doing that, now you've got, so the example similar to the last one is there a difference between men and women, males and females, between diabetes and heart disease? So in other words, we're going to look at two relative risks. You've got a relative risk for men, diabetes compared to not diabetes, what's the chance of getting a heart attack? And for women, the same thing, diabetes against no diabetes, what's the risk of a heart attack? So we've got two relative risks, diabetes compared to non-diabetes, and we want to compare them. So that's the more interesting context, and that's what I'm going to concentrate on. Now, you've got two scales of comparison where you can do this. There's the so-called absolute or relative scale, or as mathematicians would put it, would be additive or multiplicative scales. It's pretty easy to understand what that means. You've got let's think R is the relative risk. So we could have the relative risk in men minus the relative risks in female. Or for the trivial case, it'd just be risks. It's just the difference between the two. The relative one is what I've just been talking about, which is where you do one over the other, either females over males or males over females in terms of the risk or relative risk. Now, unfortunately, the results are going to come out to be very different. I'd recommend that anybody who's doing analyses like this should look at both scales. You probably want to have one that's the one that you mainly talk about if you're writing it up as a paper, but you shouldn't ignore the other one because it has its own sort of utility. And when I say about utility, a lot of epidemiologists say that the additive scale, the absolute scale, is the only one that really is really useful, because they argue that if you say to take a simple example, if you say to a man, your risk of a heart attack is blah blah, he knows what it means, but he doesn't really care too much about the relative risk situation, male compared to a woman of the same age, let's say. So most or not most, I shouldn't say most, a lot of epidemiologists think that the additive scale is the one to use. But in fact, the trouble with that is, as again I'll talk about later, that's not very transportable from one situation to the next. It's too variable, too much heterogeneity. But the relative risk happens to be fairly transportable. So what I mean by that is, if you find a relative risk for, let's say, well, like I said before, heart attacks in Australia, you could be reasonably sure, diabetes compared to not, you can be reasonably sure that same thing is going to be relevant if you go to a country, let's say Malaysia, to do the same sort of analysis. I mean, it's not going to be exactly right, but it's going to be at the same sort of order of magnitude. So, I'm going to demonstrate now why they're so different. And this next graph I'm showing here. Oh no, I'm not showing it yet. Okay. I've got to define what a rate is first. Sorry, I forgot. So I've talked about the risk. The risk is, as I said, it's the number with an outcome divided by the number that you start with. So take all you in the room, in 10 years' time, how many of you have had a heart attack? Sorry, nasty example. That would be the risk. But the rate tries to take account of the fact that people will drop out. So people will drop out because they emigrate, or they could drop out because they've had a death from some other cause. So anybody that's familiar with doing medical research in populations will know what I mean. So the rate takes account of that dropout, censoring as some people call it, by taking the outcome over the number of person years at risk. So you take every person And if they've dropped out the country, left the country, after 9 months every year, you only count them for 9 months, and add all the person years together. So it's a pretty easy definition. Most easily, you find that with using Poisson regression. There's other ways of doing it, but that's the easiest way and the most common one. And then the relative risk, I talked about already, I think I can say that. But in terms of censoring, that's why I put this slide in, there's an analogous thing with censoring with relative risks, because there you've got dropout again, but you usually use the Cox model when you're looking at the ratio of risks. So instead of looking at rates with a hazard ratio, you're looking at the risks. And we use Cox regression, as I've said. You could actually use Poisson regression as well, as it says at the bottom, but the Cox model is more flexible. The Poisson model has an assumption of a Poisson distribution, which is not always quite right. So the Cox is the better way of doing it in general. So this is the slide I was going to get at. And this, I think, illustrates the problem when you're looking at the two different scales. So what I've got here is, as it says at the top, I've looked at the relative rate and the rate difference for coronary heart disease by age group. So we've got on the horizontal axis, I've got the age, and on the top axis, I've got relative rate on the left side and rate difference on the right-hand side. So we're looking at the risk difference on the right-hand side, because it's the rate difference here. As I said, it's similar, the risk and the rate. And on the other side, I'm looking at the multiplicative scale. What I want you to see is, first of all, if you forget about the male and female lines, you can see that as you age, the risk of getting a heart attack goes up. This is a data set of about 1 million people, so we can look at it in quite good detail. It's almost a linear scale. And this is even on a standard scale too. On an exponential scale, it would look better probably. If I look at the relative risk, on the other hand, that's the ones I've labelled on the left-hand side, you can see that it comes down. So the rate goes up, or risk goes up with age, which you all know, but you probably didn't know that the relative risk actually comes the other way. So they're going in absolutely opposite directions. So that's something you've got to take account of in the first place. But then when we look at sex differences, if you look at the way that the dotted and the solid lines go, different types of lines, females have got higher relative risks, but they've got lower risk differences. That the risk difference, sorry, I didn't read that out, but hopefully you've read it. It's current smokers compared to never smokers. I omitted by saying that. So the risk difference there is the difference between a smoker and a non-smoker. That risk difference is higher for men than it is for women, and lower when you look at the relative risks. So it's a complicated situation, even without looking at sexes separately. So that means it's really important, as I've already said, to show both of them in any work that you do. Now, to give an example of this, to make it a bit clearer, I hope, I've picked some data from this paper we did a few years ago using the UK Biobank. So in this paper, we looked at sex differences in several risk factors, but I'm going to pick out as an example type 2 diabetes. So it's 500,000 people, as I said a moment ago, I think. When we look at the rates by sex to begin with, so we looked, as I said, a lot of different risk factors. There's more than actually on this page even, but I've just taken this obviously from the publication. If we look at type 2 diabetes, there's the rates for women on the left-hand column and men on the right-hand column of the results. It's the rates per 10,000 person years. So you can see it's 15.6 in women and 29.4 in men. So higher risks or rates in men than in women. But what we want to see is how that compares with people with no diabetes, because that's the contrast that we're interested in a sex stratified way. It's about 8 for non-diabetes for women. And if you think about the 15.6 down there for type 2 diabetes, and the 7.95, which is about 8, as I said, the difference between those is about 7, isn't it? And if we look at the results for men on the right-hand side, it's 29.4 compared to 22.06. And again, it's about 7. So actually the risk difference on the additive scale, there's no sex difference. Now, if we then look at the hazard ratios, so this is looking at on the multiplicative scale now, the same thing, except here you've got a control group ready-made for you, which is the people with no diabetes. So it says here type 2V no diabetes. The result for women is 1.96, and for men it's 1.33. So there's a big difference between the two. You can see the relative risk for women for diabetes compared to non-diabetes is much higher than it is for men, which could have implications for clinical practice, of course. Now, all that does is just tell you that there's a difference. But what I'd like to be able to do is to quantify that difference, because I think the effect size is what, to me, really can influence people, as I've said earlier on. If we use traditional statistics, the sort of stuff I learned when I was doing my first year statistics at university, when you get interaction introduced to you, and it's probably the same in medical school, I would imagine, you're told that you should fit an interaction model. So all that means is that you get your, when you fit your statistical model, you have the two main effects, which is, in our example, it's running through diabetes, sex, and then you put the interaction between diabetes and sex. And you're told then to take the test statistic from the interaction from the results table. So you often find people will do that. So they'll tell you the male result, the female result, and the p-value. But as I said, I don't like the p-values too much because they don't tell you what the difference is. If we go back to that previous slide, you can easily work it out because you can take the 1.96 minus the 1.33, or do the division of it if you like to do the ratio of relative risk, which I like. You can easily do it for yourself, but you wouldn't get the confidence interval that way, so you're not going to get the full picture. So what I want to do is to make sure I have a way of actually getting not only the estimate, but also the confidence interval, whether I'm looking at relative risks or risk differences. That's what I'm going to do in a minute. My word of caution there is, though, another thing which is one of the things that people don't always do. If you're adjusting in your models for a lot of other risk factors, so you're interested in diabetes, but you say, well, I want to make sure I've accounted for, let's say, social differences, but most importantly, age differences, because age is, to me, a crucial confounding factor, at least in cardiovascular research, when you're comparing men and women. But it's in many things it is, because women live longer than men. If you're using confounding variables, if you're fitting them in model, make sure that all the other factors have their sex by factor interaction terms in the model as well. So it's not just diabetes, sex interaction, and then you put age in the model to get rid of the age effect. You've got to put the age by sex interaction in the model as well. Because if you don't do that, you're not reducing, you're not going to be able to fit the correct model, because you want to know whether there's an effect of sex on the effect of diabetes, taking account of other risk factors. And unless you put the sex interaction with the risk factors, you won't be able to find that. So it's crucial to do that. It also means that if you do that, you only actually need to fit the interaction model anyway, because you can work out the main effects from the interaction model, but that's a bit more complicated to explain. Ratio of relative risks, I mentioned a minute, which is my preferred way of doing it, is just to do the ratio. as I just said. Just compute the ratio. That's your estimate of the effect. So there, I've already done that for you. Type 2 diabetes increases the risk of MI in women by the 1.96 over the 1.33, which is 1.47. So that means it's about roughly half as much more in women and men. In other words, for both sexes, diabetes increases the risk of heart disease, but for women, it increases it by a factor that's 50% higher, which is quite considerable. And it's pretty amazing you find that, actually. And that's from the UK Biobank, but as I'll show you in a minute, we found similar things in other studies. But the bottom line is all that's saying is basically you don't need to do anything new to do this because you're going to be fitting the interaction model anyway to get the p-value. It's just that people don't usually take account of the terms in the model. They just look at the p-value. But be careful because sometimes some computer packages will give you results on the log scale, and you may need to raise to the power e to get back to the raw scale. Some packages, like Stata, for example, let you say which scale you want it on. I don't think SAS does that, from what I remember. Anyway, you've got to just be a bit careful that you're actually finding estimates on the real scale. But it's easy to see just by looking at the numbers. If you find a minus something or other, you'll know you're not doing it on the raw scale because you can't have a negative risk or relative risk even. So the women to men ratio of hazard ratios. So here we are for the UK Biobank paper, going back to that. And you should recognize that 1.47, I hope, on the right-hand side down there in the red ring. And I've got a confidence interval for it now because I've taken it from, I think it was Stata that was used for this, as far as I remember, taken it from the Stata model directly. So we've got a way now of actually seeing whether what the effect of sex is. It increases the relative risk, I should say, of diabetes compared to non-diabetes. But also we can see that the range of that increase is between 16% and 87%. It's a fairly wide range, but it's all positive. So if you really like p-values, you can say this is significant at the 5% level because it's 95% confidence interval, which is approximately true. Okay, so that's the basis of, I think, how you should do the analysis. But I'm going to just go over a few things that are mistakes I see people make, or at least not necessarily mistakes, but shortcomings, let's say. Now, a common error, which Cara touched upon with one example she gave, is that people use the sex-specific results without looking at the interaction effect, which I've just been talking about. And if you get something like this, where you can see, if you look at that little table there, again, these are real data from a different example. It's unpublished data. It's not for diabetes, but anyway, it'll do as an example. And they're real numbers, so I've not made the numbers up, just the application. So for men, the relative risk here is 2.63, and for women it's 3.26. And you'll see from the confidence interval that the women one is significant. And often people put significant things in bold, which is what I've done there, although personally I would never do that, but that's what people often do. So what they would say then, okay, that means this diabetes only got an effect in women, not in men, which is absolutely stupid. I mean, it's stupid. In men, if this was a real example, it's 2.63 times the risk in no diabetes. How can that not be an effect? I mean, it's huge, more than double the effect. But people will do that sort of thing and say, it's only women where it really matters. So, of course, what I want them to do is to add that extra column on the end there, excuse me, and find the ratio of relative risks. So I've done that here. It's 1.24, and it's highly non-significant because the range of excuse me, 95% confidence interval goes back to 0.36. I mean, huge confidence interval. So you can't say anything that there's any real sex difference. It happens that we've found in our case a higher relative risk for women, but it's probably just chance. Or at least you can't rule out the play of chance. Okay, so meta-analysis then. I promised I'd come back to looking at that. So why would you want to do meta-analysis? Well, it's pretty obvious. You want to overcome the problems you have with a single study, which has got both limited power and it's in one specific environment only. So we want to get the best evidence. Sorry, it's the other one. Sorry, I don't know why I hesitated then. To get the best evidence. You want to get the best evidence you can. And the best way to do that is to take all the evidence together and synthesize it in some way. It doesn't have to be meta-analysis, of course. You could do systematic review. And obviously, I wouldn't be saying that you can only do quantitative comparisons, because if it's not quantitative, it doesn't matter. It's still good evidence. But it may not be as good as something which is quantitative, but only maybe. So how are we going to do that? Well, first thing to do is to check whether somebody hasn't done what you want to do now before. If they've done it 10 years ago, maybe it's worth doing it, but if they haven't, probably isn't worth doing. You should also post the protocol. Prospero is the one which most people use these days. It's not the only one. That's a way of sort of registering your protocol before you start, so you don't get accused of doing something after the fact, data-driven. You don't need to do a systematic review, as I just said. Now, to do the systematic review that's going to lead to a meta-analysis, it's not good enough just to get the estimates. You also need the confidence intervals, or the standard deviations, or standard errors, or something similar. You could use quartile differences if you really have to, but it's not as good. So you want some measure of variability is what I'm saying. Because if you don't have the measure of variability, you can't do a proper meta-analysis. You couldn't do a weighted meta-analysis anyway, at least not using standard weighting tools. So look for something where you've got some measure of variability as well. A paper or a grey literature result which has got confidence interval. And again, bearing in mind that you want to not be being criticized for doing something that's driven by the data, I think you should say before you start whether you're going to do a fixed effect or a random effects pooling. So fixed effect is a singular, random effects is a plural. Because with a fixed effect, if you're not sure what that means, that assumes that there's a single result. Let's take the relative risk for diabetes to not diabetes for women, let's say. If you think that there's a fixed effect which works, the same effect, I should say, for every place you go to, every age group, every, I don't know, racial group or whatever it is, then fixed effect is what you should be doing, if that's what you believe. Because then you're saying the only variability is in terms of the sampling error in any particular study. Whereas a random effects, what that says is, well, we're not sure it's going to be the same in every environment, every jurisdiction. You allow it to be, if you think of a continuum, you could have a continuum of effects, which is the real thing for that particular environment. Within those, they've got sampling error around them, sort of like normal distributions, if you like, around them. But the point is, it's a different truth in each place. And all you're doing is taking the averages of all those truths. So this is what the fixed effect is what I call the Oxford model, and the random effects is the Cambridge model. But that's because I'm from the UK. And having been to Oxford University, or worked at Oxford University, you'll be surprised to hear that I like the random effects. Okay, anyway. So let's go back to the diabetes example again. So now when we did this was actually done before the UK Biobank example I just mentioned. And in fact, when we did this analysis in it was published in 2014, there wasn't that much data out there on sex differences. You know, it's really amazing the way it's mushroomed in recent years. And I like to think partially that's because of the work the George Institute's done, but of course I'm bound to say that. But I think it really is amazing the way it's ballooned. At that time, anyway, we could find 64 cohorts, which wasn't bad, but it wasn't 64 different publications, because some of them were themselves pooled analyses, which we had published, I have to say, and getting them for 900,000 individuals and 28,000 coronary events, so a lot more than in the UK Biobank, which was 500,000, as I said. Now, doing the systematic review, obviously we needed relative risks for both women and men, because we're doing sex differences. We had to have a measure of variability, as I've already said, and we decided that we were going to have a rule that we had to have adjustment for age. So if a paper had only published like table 1 type things, where they give you the number of women and men who've had heart attack, you can work out the relative risks for that, but you wouldn't get anything which adjusts for age, which we felt was important because of the fact, again, that women live longer, and as I showed you with my graph from the cancer study in the US, the relative risk changes a lot with age. Anyway, this sort of a diagram is common in systematic reviews, as I'm sure you all know. When we got down to 22 studies, as it says, so I told you it wasn't a great number of studies. Anyway, here's the results. So with all these studies here, some of them you may, if you can read it, you may recognize, but they're a bit dated now, as I said. Over on the right-hand side, I've written down the relative risks for women and men. And you can see again that women have got a much higher relative risk than men, as we found in the UK Biobank. At that point in time, no studies had estimated the effect of sex on diabetes, coronary heart disease ratio, rather than the p-value. So come back to what I was saying a few minutes ago. Estimating the effect size, I think, is important. But when we did this work in 2013, nobody, including our own publications, which is a couple of them in there, nobody had ever had published what the sex difference was. Again, you can work it out by doing the ratio, but you can't get the confidence interval. Again, I'd like to think that because of the work we've done, that's becoming more common now. So I find people are quoting the ratios of relative risks, which they didn't do 10 years back. Anyway, if you don't have it, and if you're using historical data, you won't get the ratio of relative risks. How are you going to get that? Relative hazard ratios I've put here because they were hazard ratios just now. Right, now you'd be delighted to hear that at this point we break into statistical theory. Are you kidding me? That's my the balcony for my apartment in Des Moines. We had a cockatoo and a corvid of some kind on there this morning, but the rainbow lorikeets are far more cute, aren't they? Anyway, he's got he doesn't want to hear about sex theory, statistical theory. There's the statistical theory, but I don't want you to read it because it's irrelevant. All this is saying is that you can work out the relative risks, the ratio of relative risks and the confidence intervals from the relative risks and confidence intervals. So you can do it, and in my sort of tutorial paper, which some of this talk is based upon in heart, I actually have this Excel form as one of the supplementary files you can get from Heart, which is the journal that published it. So all you have to do with this is fill in for the different centers, for all the different studies, for women in the red and boys, of course, in the blue. You just fill in the numbers, the relative risk and the confidence interval, top and bottom. And lo and behold, over on the right-hand side somewhere, you get the ratio of relative risks and the confidence interval out of it. So that's the easiest way of doing it. Now, when we did that for the paper I'm talking about, that's the way we did it in the paper for the meta-analysis I'm talking about with diabetes, we got the answer of 1.44. So that means that, similar to what I said before, the effect of diabetes is 44% higher in women than it is for men in terms of heart disease risk. And I've summarized these data here. So as I said already, heart disease is on the left-hand side here. I've done stroke on the right-hand side because we did a similar thing for stroke later on. As I said, having diabetes increases the risk for both sexes, but it's 44% higher for women than it is for men. And then for stroke, you can see it's less than that. The risks, the relative risks themselves are lower, but also that means diabetes has got less effect on stroke as it has on heart disease. But the ratio of relative risks also is lower. So it's 27% extra, but it's still, 27% is really significant in the general English sense of the word. Okay, I better come back, I think, because I've said to you that you should look at risk differences as well as relative risks. But as I said before, I hinted about this, the trouble is if you want to do meta-analyses later on, remember I said that they're very useful for sort of papering over the problem of having a too small a sample in the first place. If you really want to do that, it's a bit difficult to do it with risk differences. First of all, they're rarely quantified. But most papers, if you look at, certainly for the clinical trials literature, you never see risk differences, or very rarely anyway. Sure, you do see numbers needed to treat, which is really, it's a type of risk difference. But they never really, can't think of any I've ever seen where they look at risk differences. Risks are often shown, so the data is not going to be there to do meta-analysis, basically. And the trouble is, it's different for every place you go to. And that's because the risk is so different from one place to another. It depends, things like the health service. I mean, if you're looking at the risk of cardiovascular death, it's going to be way different in a country where you've got a good medical system, or if you take the US, for example, in a democratic state where they've got the Medicare and Medicaid, both Medicaids, the below, anyway, sorry, I don't want to go into the American system, but some states of America have got a good system, let's put it that way, and it's always the democratic states, interestingly, I wonder why. If you look at the risks there, they're a lot lower than they are in the Republican states. So there's no way you're going to pool the data together as you could with relative risks, because the relative risk might well be quite similar, again, thinking of diabetes compared to not diabetes. So they're not amenable to meta-analyses, and you can't get the data from published publications anyway. So they're not so good in that sense. What you can do, and it's usually a good idea to do this, is to take the risks from the original paper, which are often in things like Table 1 or Table 2. They give you the risks for the two different sexes, and you can use that in a meta-regression to see how homogeneous your relative risks are, or ratio of relative risks as well, compared to the background risk, which is what the risks are really telling you, the background in the population being studied. Okay, so just going to finish by thinking about when people think they've accounted for sex, but I don't think they have. So when is it that somebody could say they've accounted for sex, and they haven't? Now, I talk from experience here, because I say to people, have you taken account of sex? Yes. It's in Table 1 of the paper. Thank you very much. Table 1 of the paper, okay, that's your study population. It's lovely to see that, fantastic. But is there a difference in the effects of what you're interested in by sex, which is what I'm interested in? So that doesn't account for sex. Second thing is, yes, we've adjusted our hazard ratios for sex. Cara mentioned this. Adjusting, you should think of adjusting as getting rid of a nuisance. You don't really want to do adjustments, you'd rather have a pure comparison. But you put these things in like age and blood pressure or something because they're a bloody nuisance. You just want to get rid of them, so you stick them in the model. If you've adjusted for sex, you've got rid of the effect of sex. It's the absolute opposite of what we want. We want to take account of sex, at least I do anyway, I think you all do. So you shouldn't, having it as a confounder, an adjustment variable, is doing exactly the wrong thing. So that doesn't account for sex. We were on a call in the UK about a year ago now, where it was before the message study got going, talking about why we needed sex and gender research. A meeting like this today, and some man, I'm sorry to say it was a man, he said, "Oh, I don't know why you worry about it. All you've got to do is reweight. You've only got 20% of women in your study. Just reweight. Count that as a greater weight than you would otherwise." All that's doing is just adjusting for sex again. It's not giving you. You can't get any more information by doing a posteriori weighting to it. Obviously you can't. I mean, if you could do that, you'd only have to have a sample of 1 for anything and just weight it up to 1 million for the population. It's absolutely ridiculous. But anyway, that's what he said. One of the good things about getting older, by the way, is that I like it when people say, like they did this morning, that the sort of the bogey person is the middle-aged white male, because I'm not middle-aged anymore, so I can it's fantastic. And they also say sometimes we've shown when they have, they don't say this, but when they've shown the outcome results by sex, but they haven't actually taken any comparison into account or even discussed what they've done. And this happens all the while. And just to give an example of this is my penultimate slide, you'll be glad to hear. We did this survey. Is Laura Hallam here? She's not, is she? Laura Hallam was a student we had, a very gifted young woman. Anyway, she did this as part of her master's degree. She looked at the 10 highest cited Aussie medical journals in 2020. So she picked out 1,136 articles, which is a heck of a job to do. And what we've got in this diagram here is a little bit complicated because it's a bar chart, but the denominator is different for everything I'm looking at. So I need to explain it a bit, which I'll try. I won't try and do every one, but this is looking at the percentage. It's a percentage of, if you like, the ones at risk, if you think of it in a sort of clinical way. So, for example, the second pair of columns, forget about the colours for a minute, this is where the number of journals, articles of those 1136 actually had multiple sexes. So it's almost 100%, because those two bars are almost 100%. There's only about 4, 5, something like that percent who was single sex. In the next column, it says justified single sex. So of the few that didn't have two sexes, not all of them actually justified why they were only doing a single sex. I mean, obviously, sometimes it's obvious. We take, of course, if it was something which could only affect a man or a woman, like prostate cancer, for example, we took that to be justification. But I mean, these are ones where they had like heart disease, and they could have justified where it was only in women or only in men, whatever. The next one, the very low bars, is where the methods were described. What that means is when they told you how they defined sex and or gender. So only 2 papers, I think it was, maybe 3 papers actually, 3 papers out of the, no, maybe a few more anyway, so a very, very small percentage anyway, said how they defined it. We talked this morning about definitions of sex and gender, of course. The next pair of columns talks about when the results were stratified. So you've got the second column, which is, it was about 95% of papers had multiple sexes involved, but of those, only about 30%, less than 30%, stratified their results by sex. So although they had both sexes, they didn't report them separately. The next pair of columns is where we allow them to say whether they justified not reporting, not the stratification, that is, and very few did out of the 100% that could have done. And finally, the last one was discussion. So of the ones that had stratified the results, what percentage had actually discussed those results? And again, it's a very small percentage. So this is this is fairly recent. It's only 3-4 years out of date, but that's the situation in Australia. And furthermore, what makes it even worse is the green is for the people, the journals, I should say, which are using the International Committee of Medical Journal Editors guidelines, which say you should report sex and gender. And for all of those categories I've looked at, you can see there's very little difference between the greens, where they have got the guidelines, and the purples, where they don't have those guidelines. So that shows you that we can talk all we like about introducing new policies, NHMRC or whatever, but unless you actually have some way of making it mandatory, or at least giving a good stick to the carrot, you're not going to solve things, because it's a great example of that, I think. And it's Australian data, which is nice for this particular meeting. So my last slide is just a summary of the necessary steps in what I call evidence generation. So this is from a paper that Sonna Peters and I wrote, and it's a roadmap, we called it. We wanted to call it something else, but what was it, a strategic plan or something, but somebody already published that. So we called it a roadmap, which is horrible, isn't it? Anyway, it's a roadmap for sex and gender research. Doesn't say anything new. When possible, aim to include an equal number of men and women for the sake of equality, if nothing else. Produce results of study outcomes by sex and or gender. So produce them and quantify the differences, which is what I've just been going into. And report the outcomes by sex and gender and interpret the degree of difference. That's like the confidence interval I meant. And reporting them, by that I mean laying it out so other people can use it in the future in meta-analyses, or indeed to help change guidelines. Right, thanks for your attention. So, questions? We've gone over time, but we started late, so. I mean, it's a great question because it's really difficult, isn't it? You've got, I mean, I always think of the issue that you'd have anyway with a clinical trial, for example, that is always ignored. I mean, they say you've got to have, people use a past data to fix what the background risk is going to be. But they don't say whether that's the risk in men and the risk in women. And if it's, again, most of my research is in cardiovascular area, so talk about that. If you really took account of the fact that you want to have, I think I've basically said this, 50% men and 50% women, you'd have to say, well, I've got to have a much larger sample of women than I have of men, and then you get into the problem of saying, well, maybe that's equitable, but it's not equal. If you think of the equality, equity differential. I mean, the short answer is you've got to just be honest, I think, what you're saying. And if you're really going to power it properly, you're going to need a much larger dose of money, and they're not going to give it to you. So what can you do? The NHMRC will come out, I'm hoping they're going to come out if they're not already, by saying you should have men and women in every study, but I don't think they'll say you have to have half and half. They might, I don't know, but again, if you take a silly example like cancer, breast cancer, as I said, you couldn't do that. So I'm hopeful that the rules won't be too stupid, let's put it that way. I'm sorry, it's not a very good answer, I know, but I'm very aware of the problem.
Thanks, Mark. That was fantastic. The question I have maybe feeds on a little bit like from the previous question, and it's that when you're considering sex, you're clearly considering it as a binary variable, which my simple brain can follow. But what Cara was talking about this morning is that obviously the spectrum of gender and possibly even biological sex is not binary. And I just wonder if you have any thoughts about how, as a research community moving forward, we're going to be more inclusive with the gender side of things as well as the male-female. Is it going to rely on the fact that we're all eventually in another 5, 10, 15, 20 years' time going to be able to pool meta-analyses and have enough of the smaller categories of gender to be able to look at specific effects there? Or is it going to require a totally different methodology? And these approaches, I mean, we're never going to reach sample size in the traditional statistical sense for people who and not identifying as man or woman. I don't know whether Cara afterwards might want to have a thought about that as well.
Well, Cara did mention it. I mean, you can oversample for, I mean, that's been done for years for things like age, to get enough people. I mean, the 45 and up study here oversampled old people. So it's not difficult to oversample to get people in. And you're talking about the non-binary elements of sex and gender. Analytically, it's not a problem. It's just the power is going to be awful unless you oversample. But I mean, again, the practicalities are obvious. Intersectionality is the same thing. You know, if you want to have intersectionality, you've got the price you pay for it is the price, literally the price, a money price. I'm not really sure there's a way around it except by saying, as you just acknowledged, we can do meta-analyses later on.
Yeah, I'm happy to chime in there. I mean, what's the cost of not including people? And I think Laura showed very clearly this morning that the direct and indirect costs of not including people and being able to offer them the treatments that are right for them can be quite significant. So there is that argument, and I think right now the gold standard is to report the raw data so that it can be used in a meta-analysis. Unless, what's your hypothesis? Are you taking an intersectional perspective? Is your research designed to help populations that have been marginalized before? And I mean, Prue, I can't speak for you, but certainly in Canada, I have yet to see a reviewer reject an application because you appropriately justify that the event rate might be different in, I don't know, women and men, and that you want to make sure that you capture the effect. So if this is high quality, rigorous science that's well justified, I mean, if you have more variability in one population than another, then yes, your sample size, I guess estimates should take that into consideration. And like Mark said, be honest, explain, make it substantive, make it hypothesis driven, explain why you're doing it. I think getting away from just the rote, oh, they want me to do this, should I do it or not, is not the way to go. But I don't think anyone's ever been told they can't have the money if it's an excellent study that's going to help different populations based on preliminary data that suggests the treatment might be different. So I don't know if that helps, but I think you're on the right path.
Okay, we've had a long day, so thank you for your attention.